Okay, next up we're going to be talking about tangent graphs. And tangent graphs are a little bit easier to deal with, and you'll see why shortly. The tangent function is one of the trigonometric functions whose graph has asymptote lines. And if you don't remember what an asymptote line is, it's a line that a graph gets closer and closer and closer to, but never crosses. It says graph the function below and show the asymptotes. And now normally when we talked about asymptote lines, we're talking about rational functions, functions that involves fractions. And tangent actually does involve fractions. If you don't remember, tangent is equal to y over x, which we know that y is sine and x is cosine when we're talking about the unit circle. So we do have a fraction. And anytime we have a fraction, the bottom of that fraction cannot equal 0. So I want to show you with Desmos that actually anywhere that cosine is equal to 0, you're going to have what's called an asymptote line. And here we see the graph of what tangent looks like. Tangent is very different from sine and cosine. We don't have to worry about amplitudes because tangent actually extends up forever. And notice how it's getting closer. Each of these lines of tangents gets closer and closer and closer to the line next to it. And those are going to be your asymptote lines. And we can see that with cosine. Notice where cosine is equal to 0. At all these places where I'm putting dots. Anywhere cosine is equal to 0, notice that your graph for tangent gets closer to those points, to those x values, but it never actually touches them. Those are your asymptote lines. So let's take and draw a graph of our tangent function. And notice that we're going to put those asymptote lines everywhere our cosine value is 0. And there are those asymptote lines. And now to actually draw the tangent function, it's pretty easy. All I do is I put me a dot. I know the tan of 0 is 0. And I follow the asymptote line up. And I follow the asymptote line back down. Just to give me a rough sketch of my tangent function. I also know the tangent of 180 is equal to 0. And I do the exact same thing there. I follow the asymptote line up. And I follow the asymptote line there, and I just repeat that process for the other two or three areas. And there would be your tangent graph. I do want to also remind you that tangent is a periodic graph. It is the same graph over and over and over. However, the period's slightly different. Now, amplitude, like I said, not applicable. Tangent does not have amplitude, but it does have period. Notice that how long does it take? Okay, we're down here at the bottom. We go back to the top. How long does it take this to repeat? The distance from here over to here is actually not the same as what it was before. Or you can measure maybe the middle over to the middle would probably be the easiest way to measure it. That's 0 over to pi. The period for tangent is actually pi, or only 180 degrees. And that's going to be very important to us later on, especially when we're solving trigonometric equations. So we very much need to remember that. So sine and cosine had a period of 360. Tangent has a period of 180. Now let's talk about changing the period and the asymptote lines for tangent. So given that y equals a times tangent of b theta, now b is going to be very important to us in these, where theta is in radians. The period, for the exact same reason. Now, normally the period is pi, or 180, but if you multiply by a factor of 1 over b, again, we reciprocate this to see how much it's compressed, okay? So this, if b is what's being multiplied by our x value, or our theta value in this case, then 1 over b is going to be what our actual scale factor is. The asymptote lines are actually going to occur here. They are at the odd multiples of 180 or pi over 2 times the absolute value b, and we can use that to actually find our asymptote lines. So let's try some of these. It says identify the period, then graph each function. So again, normally our period's 180 or pi, but if there's ever a value being multiplied by our x, we know that's going to change it, but in this case, there's not. So pi, or 180 degrees, is going to be our period. Now, I like to go ahead once again, and let's go ahead and let's go ahead and graph those asymptote lines before we get started. And since our b value is 1, let's go ahead and write that again. Our asymptote lines will be located at pi over 2 times the absolute value of b. Now, since our b value is 1, we don't have to worry about that. So it's going to be the odd multiples of this. So 1 pi over 2, 3 pi over 2, 5 pi over 2, -1, -3, -5. That's where our asymptote lines are going to be located. So pi over 2, 3 pi over 2, 5 pi over 2, negative pi over 2, -3 pi over 2. Let's go ahead and draw those asymptote lines. Now next, what we can do, we always know because of the rotational symmetry of tangent that it's always going to cross. It'll always have an x-intercept or a 0 right in the middle of those asymptote lines. So there's going to be our x-intercepts. We can go ahead and plot those. And what I would do next is I would actually probably plug in another value here. Maybe this is 90 here. This is 45 degrees. So maybe plug in 45 and just see what you get. Because we know that we can find the tangent of 45 really super easy. So 45 degrees, tangent is 1. 2 times 1, that's going to give us a value at 2. So when we have 45 degrees, we have a y value of 2. We can actually use that symmetry and come over here at -45, and it'll be -2, and just kind of use that same pattern to plot some more points over here in each of these areas, and then simply use that to connect our dots, and we're going to have our graph. Let's go ahead and connect them. And there's my graph of y equals 2 times tan of theta. Now, we do know that this 2, we didn't talk much about it, but it did stretch that thing times 2 vertically to make it a little bit taller and skinnier. Okay, number 2, y equals 1/3 tangent of theta. Or tangent, excuse me, the tangent of 1/3 theta. Now, notice here that the 1/3 is now actually on our x value. So that's going to be a horizontal stretch. And we've got to flip it, though, of horizontal stretch times 3. And we know that our normally our period is pi for tangent. However, if we're going to stretch it 3 times wider, it's now going to be 3 pi or 540 degrees. Now notice that 540, that won't even fit on our graph here, the asymptote lines. Well, actually some of them will, but it's going to be super wide is what I'm trying to get out here. So to actually find those asymptote lines, here's what, honestly, I feel like it's a little bit easier. Normally, your asymptote lines are at 90. Every 180 degrees be 270, and so on and so forth, and also -90 and -270. However, if you stretch them 3 times wider, it's a little bit easier, I feel like, to find it this way. If you multiply each of these by 3, it's giving you -270, -810, and also, if you had +90 and +270, which is where the other ones are located, you'll have +270 and +810. So you're going to have, that's where those asymptote lines are going to be. 270, 810, -270, -810. Let's go ahead and plot them. And there you see those asymptote lines at -270, +270, 810 is not going to fit on there. We know that our tangent graph is going to cross directly in the middle. Again, we can plug in some values if we'd like to see where some other points on your graph are, or if you just need to sketch a graph, you could just come out here and you could follow that asymptote line up, and tangent follows it down. So our tangent graph is going to look something of that nature, and you could kind of sketch out, you could kind of repeat that over here and do the same thing up here. We know it's going to come down like this, so our tangent graph will look something of that nature. Okay, we're going to do 2 more of these. On this one, we do have a vertical compression and we have a horizontal compression as well. The 2 is the only thing that's going to affect the period. Again, normally the period of tangent is simply pi, but we've got to multiply that pi by half. So that's going to be pi over 2, or we can call that 90 degrees is going to be our period. Again, normally your asymptote lines for tangent occur at 90 degrees and 270 degrees. However, if we multiply those by half, they are now going to occur at 45 degrees and 135 degrees. And again, you can take the negatives of those as well, and it's just going to give you -45, -135. Let's go ahead and plot those asymptote lines. And there's those tangent lines at 45, 135, negative 45, negative 135, and you notice these are going to occur every 90, so if you'd like to draw some more. And then we know that our graph simply follows, it's going to be right in the middle. It's simply going to follow those asymptote lines, so we can, if we just need a sketch of the graph. Now, we'll talk about later on, if we did have a negative there, it would have to flip our graph over. But since we're simply talking about a positive tangent, it's going to follow the same pattern as our other tangent graphs. So you just graph this over and over and over. And I'm just going to do maybe one more for you, but this same graph would follow on the left side as well. And that's going to be the graph of 1/2 tangent of 2 theta. Now you could, and I didn't, but you could actually take and plug a value in and multiply by 1/2 to get a little bit more accurate graph, but this will suffice for just an idea of what that graph is going to look like. And the last one, 4 times tangent of 1/2 theta. Again, the period is normally 180 or pi. However, we're going to have to multiply that by a value of 2. Again, don't forget to reciprocate it. And that's going to be the period of this one. So 2 pi or 360 degrees is how often our graph repeats. Normally, once again, we have an asymptote line at 90 degrees because the cosine of 90 is 0, so we know we're going to have an asymptote line there. However, we're going to multiply every asymptote line by 2. So instead of at 90, our asymptote line this time is actually going to occur at 180. And again, here's what I do. Just use the period from there. We know that every 360 degrees is where our other asymptote line occurs. So I'm going to go back 360 degrees, and our other asymptote line is going to occur at negative pi. And I believe that's the only 2 that's going to fit on our graph. And from there, we simply take and plot a point there in the middle of our 2 asymptote lines. That's going to be where it crosses the x-axis, and you can go over, that's 4 away from the asymptote, 1, 2, 3, 4. So it's also going to cross at 2 pi and at negative 2 pi. And again, if you want a more accurate graph, I guess we can do it on this one. You can take and plug a value in, like let's take a maybe pi over 2. If we plug it in and do half of pi over 2, you get pi over 4, which is actually 45 degrees. The tangent of 45 is 1. 1 times 4 is 4. So that's going to cross at 4. And we can just use the symmetry because we know at negative pi over 2, it's going to do the same thing down here. And just connecting our dots, and we're headed toward those asymptote lines, our graph will look something like this. And we can do the same thing here. We can go over 2 boxes and up 4, over 2 boxes and up 1, 2, 3, 4. We kind of have the exact same sketch here and here. Or from this dot, we can go left 2 boxes and down 1, 2, 3, 4, just to where it matches this, where we went left 2 boxes and down 4, and simply sketch the same thing there. And there's the graph of our tangent function.